Okay, thank you very much, Rifa, for your introduction, and also to Astri, and also to all other colleagues at PT Multibangan Rekatama Patria, who spend a lot of time to organize these webinars. And this is much appreciated because I think by now these are running very smoothly, and I think for anybody watching, they should find this to be an event worth attending, and also especially because at the end you have the chance to enter a quiz. We'll come to that shortly. So this is the fourth webinar in this series. And today I've taken a topic which is entitled The Practical Use of Clay Fills in Soil Structures. And I put reinforced there as well, because this is probably our main interest. But the information today could be equally applied to any use of clay fills to build, say, an embankment or a similar structure. So this is the interest today. So looking at clays and their use as engineering materials. And as I said already, in particular for reinforced soil structures. There will be another webinar in this series next month, where we'll have a significant change of topic, and we'll look at the use of CPTs in soft clays. So quite a different topic, and that'll be next month. So there is a list. So we've, in the first three of these webinars, we've developed ideas about soil properties in general. We've looked at measuring soil shear strength. We looked at the principle of effective stress. And I think looking at clay fills is an obvious continuation of this theme. And that's the reason for this particular topic today. So some pictures, some clay fills in action. So this is actually construction of part of the Jakarta Outer Ring Road using our well-known Tanah Merah. This is a clay fill of volcanic origin material, and it forms a very good fill. One reason being that it has a predominance of a rather interesting clay mineral called halloysite, which at a microscopic level looks something like this. But it's not the only kind of clay that it gets used for this kind of construction. This is using, in fact, a weathered granite material in Malaysia to build a reinforced soil structure. And here you can see them checking density as they build up the structure. Now this is an image of a soil which may be not preferable to be used as a fill. This is a clay probably with a very high content of the mineral montmorillonite, and when it dries out, you see you get this cracking, and when it wets again, you'll get a lot of swelling. Possibly these sorts of clays are best avoided as fills unless you really have to use them. And then you need to be aware of the limitations and problems of doing so. And another nice microscopic picture using an electron microscope, in this case of a marine clay. But again, you can see that kind of structure. There is a scale bar at the bottom there showing you what 2 microns looks like. So you can see that clay particles are clearly very small. What's this intended for, the webinar today? Well, we're going to talk initially about clay, and we'll talk about some soil mechanics aspects of it. And then I think really the main aim is to look at one particular point, which is the likely poor water pressure that will be inside a mass of clay fill after you've built it. Because this is vital to the understanding of the next part, which is what are the appropriate drainage measures which you should use when you're building a structure using a clay fill, whether it's reinforced or just a general embankment. As we go along through this webinar, as I usually do, there'll be these blue boxes appearing where we have some additional information, and we may be asking a few little questions as well. So this is really intended for civil engineers who have some involvement in ground engineering. That's our main target. Also, hopefully, would be of interest to more experienced geotechnical engineers. And the main target is, without a doubt, reinforced soil applications. But as mentioned already, the ideas mentioned here could be useful for quite a wide range of design applications where we use a clay fill or other fine fills. I also like to mention normally if we have some interesting books or references that could be helpful. There's one here which I've had on my bookshelf for a very long time on the left there. This was a clay fills conference held in 1978 by the ICE in London. And it contains a wealth of information about the performance of clay fills. And I still make use of the material in this book. No doubt there have been more conferences since then, specifically on that topic. But it does contain very good information, some of it which I'll be using later on in the material I present during this webinar. The other book is one of Laurie Wesley's books in Bahasa Indonesia, Mechanica Tanah, but this is the thicker one. And chapter 15 of this book specifically looks into the compaction of fills, in particular clay fills. So that's a very relevant section to the topic today. Also, from my own point of view, as a contribution to this topic, I've published two papers here over the recent years, both on the subject of clay fills, aimed principally at the conditions in Indonesia. On the left, we have a paper published at a HATI conference over 10 years ago. And then on the right, a paper published at an INA IGS seminar. And in fact, these two papers do contain the majority of the material I'm going to talk about today. So if you wanted to read this at a slower speed, or you can get hold of those papers or get in touch with me about them. But they are both references I've used today. So the content is going to be like this: a brief introduction to clays, and then we'll talk a bit about compaction, and then the relationship between pore water pressure and undrained shear strength of a clay. This is rather important. We'll then look at stress changes in clay fills during undrained loading, which is a rather important part of the jigsaw puzzle. And then perhaps the main target is establishing profiles of pore pressure in a clay fill versus depth, because this is a very useful thing to use when you try to visualize what's likely to happen as you build a clay fill and later on use it in the longer term. And that will lead to important principles concerning drainage around clay fill structures. And also, just at the end, a rather nice demonstration of what can go wrong in a clay fill structure when the drainage doesn't work as it's intended. There will be a quiz at the end that's already been mentioned, and there will be prizes for the winners. I think the first two or three. And just to make a point that the third webinar, the one we did last month, that was looking principally at the case of soils which were fully saturated. Softer soils maybe, but soils below the water table. And the main difference today is that we're now looking at clay fills, in which case they're going to be either two terms we commonly see: partially saturated or unsaturated. And this does give some differences in behavior, and I will touch briefly on that a little bit later on. So some introductory comments. Another nice electron micrograph of a clay. You can see there a scale bar of just 1 micron. Clay fills, we see many descriptions: clays, silty clays, sandy clays. But the important point is that these are materials where the content, the mineral content, is dominated by clay minerals. Clay minerals are small. They're generally flake-like, like the ones you can see in that picture there. And these materials, especially when compacted to typical earthwork requirements, would have a very low permeability, say 1 × 10⁻⁻10 meters per second. Now, this is a really small number, sometimes difficult to imagine what it really means. But in the first webinar, I came up with a different way of understanding what permeability means. So that particular permeability would be something like this: that if you watched a particle of water traveling through 1 meter of clay under a gradient of 1, it would take 320 years. So you can see that water through a well-compacted clay travels extremely slowly. Another good starting point when you're looking at clays and you're looking at a clay material with the possibility of using it as a fill would be to look at its Atterberg limits and to plot them on the famous Casagrande or plasticity chart, where we plot plasticity index, the PI, against the liquid limit. This is a really useful diagram. And I'm sure as you will know, we have a famous line called the A line, which is the thick inclined brown line going up there, and also that matches very closely to the AASHTO designations of different soil types. But what would be the important targets for clay fills? Well, you would want to have them certainly on or preferably below the A line. As you go higher above the A line, then you tend to get into the areas of soils that will be more susceptible to changes in moisture content. You'll get more swelling, more shrinkage, as we saw earlier on in that picture of that very cracked soil. So preferably below the A line. However, also, especially with clay fills, local knowledge and experience is really important. And that is something to take into account without a doubt when you're considering using a clay fill in a project, and maybe you're not so familiar with that area. Try to obtain some local knowledge about using the finer soils as fills. Some of the clays here, for example, we got London clay on there, the green, you can see the green symbols are appearing just above the A line. We'll see that one later on. We've already talked a little bit about the red clays, the Tanamera, which are the red dots. So we will meet up with some of these as we go along. So just a bit of a change of view for a minute and think about something different, because I don't know if anyone listening today has ever had a chance to make a clay pot. Maybe something you did at school, but it's fun. So what do you do to make a clay pot? Well, you start off with a big lump of clay, which you knead into a ball, and then you place it on a wheel, which you can spin. In the good old days, you do it with you do it with your feet, but probably now it's electric. Anyhow, this would spin, and then you could use your hands to create a shape as it spins round and round, and maybe even create a hollow in the middle to turn it into a pot, and then perhaps make a nice shape at the top and end up with your pot, which you then remove. And of course, you then put it into a kiln. Now, the kiln will go up to a very high temperature and will create some significant chemical changes. But before that happens, it's a question, well, how on earth does that thing stay up? It's just clay after all. And how does it stay in that nice shape? Especially when we look at the real case. There is the real situation, the ball of clay spinning on the wheel, and there is the pot before firing it. How does it retain this shape so precisely? And I think probably the answer to this is much the same as the answer to the next question, because the next question will now move to civil engineering and look at a case like this where we have a construction site, and that's a clay fill. It's actually in the west of Java. And you can see that this clay fill is supporting extremely heavy compaction plant. Well, how can it do that? There must be something going on that allows it to do that. So I thought it would be useful to do a bit of soil mechanics at this stage. And during the last webinar, I set a bit of a challenge to see if people could derive a particular relationship where we can predict the undrained shear strength based on the drain strength properties or the effective stress properties C dash and phi dash, which we have to do by using the geometry of the Moore diagram. And if we do this, we end up with this expression where you can see we have undrained shear strength on the left equals quite a number of terms there, but they're all very familiar. You need to know two things here to use it, K naught and AF. AF is the Skempton pore pressure parameter relating change in water pressure to change in shear stress. And the challenge was, can you derive this from first principles? And I'm pleased to say, yes. James Utomo did this. He sent in his derivation. It was perfectly correct. And he received as a prize the book Mechanica Tanner by Laurie Wizard. That was the shorter book. And yeah, congratulations to James on doing that. He got it perfectly right. But I want to use that expression now. So what I'm going to do, let's go back to our site and consider a depth, say 0.2 of a meter below that very heavy vehicle or that very heavy plant. And let's just assume for the time being that our water table or our phreatic surface is actually at ground level, which of course means that the clay would be saturated. And with all that information and making some assumptions about the soil properties, so typical clay properties, I put them down there in the second point, and I'm assuming a K0 of 1 and an AF of 0, which would probably be quite reasonable for that material that we saw just now. If I put all of that information into that expression, then the undrained shear strength comes out at 5 kilopascals. Now, if you're familiar with what those numbers mean, you will know that that's an extremely soft clay. Almost certain you could not walk on it. And certainly if you tried to place and compact a clay with an undrained shear strength of 5 kilopascals, it would not be possible. So perhaps to understand this better, let's now turn to typical compaction requirements that we might be using, especially when it comes to using clay fills. And the normal starting point is a compaction curve. This is something we normally derive from doing using what's called the Proctor test. And we develop a relationship between dry density of a soil and its water content for a particular amount of compactive effort. And the red line would be the result, a series of plotted points there. Now the solid black line represents the soil being fully saturated. This means you cannot go, you cannot find points plotting on the right hand or above that line. And then the dotted line represents a 90% degree of saturation or 10% air voids. So in other words, that means that the pore spaces would be filled with mainly water, but 10% of that volume would be air. And the traditional way of specifying compaction would be based on achieving a certain percentage of the maximum dry density over a certain range of water content. Now, if we did that, the limitations would be given inside that blue box. So your condition would have to be somewhere inside that box, above it and within the sides, in order to meet the requirements of that specification. And this works quite well. In fact, it's the normal way we specify compaction for granular fills, but it can be a bit difficult to apply it for clay fills. So another way of doing this, and this is really leaning quite heavily on some of the work from Laurie Wesley, but it's coming from experience of this in New Zealand. Another way of specifying compaction is to do it like this. We will require that we achieve a certain minimum undrained shear strength, which is quite easy to check. You can do it with a hand vane or some kind of penetrometer, and also a maximum air voids content, typically about 10%. So there would be our targets: undrained shear strength of 150 kilopascals and maximum air voids of 10%. Now, on this graph, I've now plotted in the yellow and green dots the undrained shear strength, also taken from different compacted samples, and the scale for that is over on the right. And you can see if we are going to restrict, or we're going to make sure we have at least 150 kilopascals of undrained shear strength, then we're going to need to make sure we stay somewhere inside this blue shape. It's a bit different now because we also want to make sure that our maximum air void content is only 10%. So it follows that S equals 90% line. Now, this is found to be a very good way to specify compaction requirements for clay fills. And I'm not sure if anybody listening today has ever tried this rather than the traditional approach, but in many places, this is a preferred way of doing it. But what we can see from this, and this is rather important, is that clay fills are going to be partially saturated. That's to say that the pore spaces will contain water, but there will also be some air. And the degree of saturation is going to be quite high. So typically in this case, it would be greater than 90%. If you had very, very low degrees of saturation, the clay lumps would become so hard you wouldn't be able to compact them. So you need to have a significant amount of water in the clay to allow you to be able to actually remold and compact the material. So what I want to do now is to take that concept of partial saturation and see how a material behaves when we load it in the undrained condition. But before we get there, I'm just going to go back a little bit to the third webinar that was last month, because I went through this procedure for a saturated soil. So if you remember, if you attended that webinar, we looked at a case where we have a soil element below a water table underneath an embankment, and we wanted to understand what happens when we apply a total stress to that soil element without drainage taking place. And the way I did this was to isolate the little element and have a very close look at it like this. And to make it a bit easier, we enlarged it like that. And then we looked inside this element and tried to understand what would go on. Now, it was quite a long description, so I've just taken part of it. And what we're looking at here is a box. And in this box, the top can move up and down. And the brown lumps are the soil particles. And of course, the blue is the pore water. And if it's fully saturated, then it's all blue. And we then looked at the case of applying a load to it. Before I get there, just to mention, we also have over on the right-hand side there, we have a gauge to measure pore pressure, the U, and we also have a tap. And today we're going to keep the tap closed because we only want to look at undrained behavior. So if the tap is closed and nothing can leave the system, then this would be the undrained condition. And then above the box, just there, I've written there the principal effective stress, saying that total stress equals a combination of the effective stress, that's the intergranular stress, plus the pore pressure, that's the pressure within the pore spaces, in this case in the water. So we're going to apply a load, sigma, on the top, or a stress. And then the question is, well, what happens when we do that? We need to restrain the size to prevent the box from breaking open. So we apply K times sigma there. And then the question we asked, this is the same as last month, is if we do this, then what's U? What is delta V? That's the change in volume. And what is K? That's the proportion of sigma required to prevent the box from splitting open. And in this particular case, we also want to know something else. What is the stress that's then transferred through the soil grains, which would be the effective stress? And in this particular situation, it'll be like this. The U value will be the same as the applied sigma. The change in volume will be 0, and the value of K will be equal to 1. And then the effective stress will be 0. And the important point is to understand why. Why is this the case? And the case is like this because in this system, the assumption is, certainly at the level of soil mechanics, that the soil particles and the water are both incompressible. But the soil skeleton itself, the assembly of soil particles, is compressible. So when it comes to sharing that stress, because the water and the soil particles themselves are incompressible, that stress all goes through the water. And because we have no space to compress the soil skeleton, it's unable to carry any of that load. So that's the situation when we apply an undrained loading to a saturated soil. This means that if we look at a possible shear surface inside there, and we consider what's the resistance to shearing on that surface, then the answer is it's 0. We're just ignoring the weight of the soil particles. So it's 0 because the effective stress is 0. No, okay, so now let's leave that little discussion behind, because that was for saturated soil. and move on to today's topic. So what we want to do now is to look at the soil element, in this case, the clay fill, which is partially saturated. So if we go back to our little picture like this, we're now interested in the particle of clay, or the element of clay inside the clay fill embankment, which we know is going to be partially saturated. So again, we'll isolate it, we'll have a close look at it, and before we add the soil, let's just think about what happens to the pore fluid itself. So I'm going to take my test box, and I'm going to fill it up with water, but this water has air bubbles in it. That's the little white things, they're air bubbles. And because of the presence of the air, it makes this, and I'm going to call it a fluid now, because it's a combination of a liquid and an air bubble. So it makes the fluid compressible, which means that the delta V over sigma is going to be something greater than 0, whereas in the saturated case, it would have been incompressible. So I'm going to apply a stress. I'm going to have to hold the box at the sides to prevent it from splitting open again. And the question again is, when I do this, what is U, what's delta V, and what is K in this particular case? And the answers are going to be like this, that U will again be equal to sigma. But delta V, if I just do it again, you see delta V is something. It's greater than 0 now because the system is compressible. And K will again be equal to 1. And just to remind you, in this case, we're still looking at the situation of no drainage. So what this means is that we now have a pore fluid which is compressible. One thing also to note about this system is that when we get that reduction in the volume of the air bubbles, it's partly caused by air going into solution. And if we increase the pressure more and more, then more and more of the air dissolves. And in fact, eventually, if we go to a very high pressure, the air dissolves completely. In other words, it's no longer present as free air. And in fact, we then return to the fully saturated condition. That would be at high pressures. So I'm now going to put the whole system together. So we now have the 3 elements of the soil. We have the solid particles, which are incompressible, but the soil skeleton itself, that's the assembly of soil particles, is compressible. And so now is the pore fluid. And the pore fluid is compressible because it's a combination of water and air bubbles. Now, at the moment, with no shear, with no normal stress applied, no external stress, what's the shear resistance here? Well, of course, it's currently 0 because there is no stress being applied. So we're now going to repeat what we did for the saturated case. We're going to apply sigma, remembering all the time that this is undrained. I'm never going to open the tap in this little discussion today. So it's undrained and we apply sigma. Question is, what happens? We have to hold in the sides of the boxes. What is U, what's delta V, and what is K? And the answers are going to be like this. Oh, and also, of course, what is the effective stress? And it's going to be like this. Now, you see, as I allowed I'll do it one more time. As I allow that sigma to be applied, you will see that there is a small reduction in volume. That's happened because we have a compressible soil skeleton and a compressible pore fluid. Because they're both compressible, the whole thing can compress, even though it's undrained. You'll also notice I made the little air bubbles become smaller. So this means that U is now going to be something greater than 0, but less than sigma. Delta V will be something, it'll be greater than 0. K is going to be K, it'll depend on the soil properties. And also, we see that there is a small increase or a small effective stress generated because there is a compression of the soil skeleton, then sigma dashed is something greater than 0. And of course, the important principal effective stress would say that the effective stress is going to be the total stress minus U. And this means that now, if we look at that possible shear surface, we find that there is a resistance developed there. So the shear resistance created by the undrained increase in external total stress is something. And that's happened because the effective stress is greater than 0. So an important conclusion from this is that in partially saturated clay fill, that an undrained increase in total stress can be shared between the pore pressure and the effective stress. And this, to say it one more time, happens because both the soil skeleton and the pore fluid are compressible. And this is an important difference compared to saturated soils. Now, I want to get another clue towards the looking at the relationship between undrained shear strength and the pore pressure in the soil sample. And to do this, I'm going to look at an unconfined compression test. This is a very simple test. I'm sure you're all familiar with what you do. You simply put your sample of clay into a machine and you load it until it fails. And what's nice about this test is that that piece of soil you can see there in the machine could just be a lump of soil ready to be compacted into your project, into your clay fill. And I'm going to look at some results published in a very famous paper by Bishop and Bierman in 1960, where they present the results from an unconfined test on remolded London clay with the properties which you can see there. And here's the result. So we have strain in the horizontal direction, and then the green dots show you the increase in deviator stress until the sample fails. And it fails at about 68 kilopascals. So that means the undrained shear strength is half of that, about 34. But what's also rather nice in this test is that they arranged it almost certainly inside a full triaxial apparatus. They arranged it so they could also measure the pore pressure. And when we look at the pore pressure response, we see that the pore pressure starts off at almost minus 40 kilopascals. It then becomes a bit higher in terms of pore pressure, and then it drops off again. So we can see that the pore pressure inside that sample is negative. So although the clay is soft, undrained shear strength only 34 kilopascals, in order to create that undrained shear strength, it was necessary for there to be an initial pore pressure of minus 38.2 kilopascals, that is to say, a suction. That suction was required to create that particular undrained shear strength. So even though the clay is soft, it's in a state of suction. So let's go back now to that particular situation on the site in West Java and see how it's going to work. So this is what we calculated earlier on when we assumed that the water level was at ground level and the clay was saturated, which clearly is not the case. So what I'm going to do now, I'm going to use my formula, and I want to get SU, undrained shear strength, to become 150 kilopascals. Now, to do that, if you look at that formula, everything is fixed except for the only thing we can change is the effective stress, sigma 1 dash, that's the vertical effective stress at that point in the clay. The total stress is also fixed. The total stress is, at that depth, the total stress is 4 kilopascals. Therefore, the only thing that can be changed to reach that undrained shear strength is the pore pressure. And in fact, we need to make the pore pressure minus 162 kilopascals to achieve that undrained shear strength. In other words, it's a very high suction. And that's what's going to be present in that clay. And that's the reason why that clay can hold up that very heavy machine, because of this high suction. It's also the reason why the potter can make his pots. So if we try and imagine what's going on that site. So there is our initial situation, and we're going to excavate the fill from a borrow pit. We have those properties we mentioned earlier on. So we dig it out and we start to place it, and we run a compactor up and down there, and we look at that particular element just now. And what we found was that it had a total vertical overburden stress of 4 kilopascals at 0.2 of a meter. And the pore pressure was minus 162, which is a suction, of course. So that was when we first placed that layer. What happens as we build up the fill higher and higher? And we're going to build this fill to something over 10 meters. So we're going to do that. We build it up. Now, in doing that, there will probably be a bit of an increase in the undrained shear strength because of the reasons I mentioned just now. So maybe that's a little bit higher now, the undrained shear strength, a bit higher than 150. But in this situation, I can use our formula again to look at the stresses and the pore pressure in that element. And the total overburden stress is now 204 kilopascals because it's 10.2 meters high. And we find that the pore pressure has just become positive. In that situation, it's just 21 kilopascals. So you can see how the pore pressure has changed due to the undrained application of the load above the soil element. Now, a very nice way to summarize this kind of data is on a diagram like this, where we're going to plot the pore water pressure along the horizontal axis. There's 0 in the middle, and it's going to go negative to the left and positive to the right. And then the vertical axis is the total vertical stress. And we can simply calculate that as the height times the unit weight. So if we just assume unit weight of around about 20 kilopascals for well-compacted clay, then we can add an axis. And we can also then calculate what's called a pore pressure ratio, which is simply the ratio of the pore pressure to the total vertical stress. And I can then plot lines of RU value like this. And you can see that we have RU positive on the right-hand side. And of course, because pore pressure is negative over on the left, the RU values go negative. And the thick blue dotted line would be a typical value of RU when we have a hydrostatic water table condition. In other words, the water table at ground level, which we assumed, if you remember, at the beginning of our exercise just now. So that's the blue dotted line. So what I'm going to do now, I'm going to add the two dots we just calculated. So the brown one was when we first compacted the clay fill, and the blue dot is when the fill reaches a height of 10.5 meters. And that's, you can see how we have just gone into positive pore pressure at the blue dot as we calculated just now. I can also add my original calculation where I calculated that very low undrained shear strength. That's the purple dot up there near the 0. And I can also add the data from the Bishop and Beerham test, which is the green dot. And I can also add to this diagram the undrained shear strength that's applying in each of those cases. And what you can see is that at very shallow depth, as you move to the left on this diagram, in other words, as your suction becomes higher and higher, then your undrained shear strength is also becoming higher and higher. And that's what we'd expect to see when you're compacting a clay fill. Now that was a bit theoretical. So what I want to do now is to look at some real data using that same diagram, and just reminding ourselves, of course, that clays are partially saturated. And what I'm going to show you is just a small sample. It mainly comes from that clay fills conference, the one I published in 1978, but you can find lots more data of this type. So we look at some laboratory testing and we look at some measurements from site. So same diagram, I don't need to explain that again, but in this case, those 4 lines are all derived from doing laboratory testing on a UK clay called the Lias clay, which is a reasonably plastic clay. And what's happened here is that a number of samples have been recompacted to achieve a certain undrained shear strength in the laboratory, and then a test is done to look at the relationship between the vertical stress and the pore pressure. And you see the nature of that curve. So the curve is heading up. So if you can imagine, if you went down to very, very small total vertical stresses, you would get very high suctions in those samples. We also see that generally then as the undrained shear strength increases at any particular total vertical stress, then the pore pressure reduces. Here's another piece of information. This is coming from construction of a dam in the UK, the Chelmarsh Dam. There was no report of the undrained shear strength value, except it was reported as being quite strong on rolling. It's a rolled clay dam. And you can see again this tendency for as you reach the top of the clay that the suction is getting higher and higher. And then the last of these examples is a highway embankment, very typical one, 12 meters high, again in the UK, built from London clay, quite plastic. Unfortunately, in this case, the undrained shear strength was not reported, but the clay was generally placed on the wet side. So perhaps the undrained shear strength is going to be lower than 150 kilopascals that we identified earlier on. And here is the profile through the 12 meters of the fill of the pore water pressure against depth. The fill is 12 meters high, you can see on the vertical axis. And this is the measured pore pressure, both in the center line and towards the edge of the embankment at the end of construction, EOC. And you'll see that in the top part, we have negative pore pressure. And then we get down towards the bottom of the clay and the pore pressure does become positive. Very much following the trend we were looking at earlier on in the rather more theoretical way. This is after 2 years, and this is after 4 years. And it's a rather interesting result here because we can see that the suction in the top 8 meters remains much the same. There is a slight change, but we also notice that the positive pore pressure in the base of the fill is reducing gradually through dissipation, almost certainly because there is a basal drain. There's a granular drain just below the 12-meter mark, and therefore we have zero pore pressure there, and the excess pore pressures are dissipating towards it. So this little picture that you see here is a very good demonstration of what's going to happen in a moderately high fill, in this case built with a slightly wet clay, when it comes to pore pressure and the change in pore pressure with time. So if I plot that information for end of construction on this diagram, it'll look like that. Again, you see that basic trend that as your total vertical stress becomes smaller, then your pore water pressure becomes more and more negative. So that's that same trend of behavior which we've seen earlier on. So just to summarize in this picture, there is our 12-meter high clay fill. The upper 2/3 is in a state of suction, and the lower 1/3 has a positive pore pressure because of the effect of the undrained loading of that clay. And of course, that is dissipating towards the basal drain. So later on, when we talk a little bit about the importance of drainage when we use clay fills, this is a very useful little diagram to remember, because you need to take that into account when you think about the planning and design of drainage systems for clay fills. So what are the conclusions so far? So we have seen that a well-compacted clay fill, certainly to typical highway specifications, is likely to be in a state of suction to a considerable height, say at least 10, maybe 12 meters. That last case, the clay was rather on the wet side, according to the paper. And it's only going to be at the base of high fills in excess of those values that you're likely to get generation of positive pore pressures. So what's the implication of this when it comes to drainage measures? And this is really perhaps the main target of this talk today is how you would go about designing or laying out drainage when you're using a clay fill. So to do this, I'm going to introduce you to a gentleman here whose name is Clay. In fact, I guess here in Indonesia, we're going to call him Pak Clay, all right? And this guy, Pak Clay, he's in a permanent state of suction, all right? So you can see him there. He's got this drinking straw, and whenever you put clay straw into free water, then the water will travel from where it is into clay in any direction. So it can go uphill, downhill, in any direction, because clay is always in a state of suction. And he prefers to be that way, because once the water goes into clay, he will swell and he will soften. He doesn't want to do that. He doesn't like swelling and softening. He wants to remain in his state of high suction. And the diameter of the straw is of importance because it's like permeability. So if the straw is very, very, very thin, then of course, in the short term, clay will not receive much water, but he will still receive some. And if we leave it there for long enough, he would eventually empty the glass. And that's a little bit like the situation when we're trying to plan drainage in contact with clay fills. So we have a little message coming from Clay here. He says, look, based on this, please could you minimize my exposure to free water because I don't like it. And that's what is worth thinking about when we talk about drainage. So these are some cross sections taken from one of my previous published papers where I'm trying to make some points about the importance of drainage when we're using clay fills. I'm showing pictures of reinforced soil structures. You can see one here. It's a modular block wall. And in the first cross section, I just want to point out some errors. And this is all was very much related to Clay and his comments just now. And there are some mistakes in this cross section. First of all, first mistake is that the drain, I can tell you, is rather small. And if the drain is very small and you've got lots of rain coming off that road surface, the black layer you can see there, of course, the drain will very quickly fill up and overflow. And you don't want that to happen. You don't want the drain to overflow. And also the facing drain, that's to say the granular material shown behind the facing there extends up to the top. In fact, when the drain overflows, that water will tend to run down that granular layer, putting it in contact with the clay fill, the brown material on the right-hand side, which is something we don't want to happen. Also, with modular block walls, one mistake that we sometimes see are low-strength frictional connections. Because if you're going to build up a little bit of pressure, swelling pressure in the clay, you need to be able to resist it by having adequate connections between the facing and the geogrid. And also we see a mistake here is that a basal drain is being used, which is often a good idea. It acts as a capillary break between deeper soils and the fill, but it's been placed below the external ground level because it's just been placed at the bottom of the fill, which is often done. But the question is, well, how does the water get out of it? We don't want to leave that drain full of water. Remember what Clay says, don't put me in contact continually with free water. So unless you have some system of pumping or a very deep drain on the outside, how do you keep that drain empty? So these are all, if you like, errors. Now let's look at the cross section, the same one, and correct the errors. So the first thing is, we'd like to have a nice big drain adequate to carry any likely surface water flows. We seal the facing drain, that's to say the granular layer behind the modular blocks, we seal that from the surface. We don't want surface water running into that drain. We want to have high strength mechanical connections just in case there is some swelling, it can be resisted by the connection. And then the basal drain is far more effective to place it at a level whereby it can easily drain to the outside into, say, a drain at the toe. And you can even consider putting in some slotted pipes, maybe wrapped in a geotextile, to help encourage that drain essentially to remain empty. So these details are really quite important when it comes to drainage for clay fills. If we look at a more general case here of perhaps a higher fill built up against a hillside where there might be some internal water flows, then the principles are much the same, but perhaps a few other things to think about. So we are expecting the upper part of that fill to be in a state of suction, and the lower part could become positive if the fill is very high. And also we might have some internal flows. But the first thing is we want to design surface water drainage adequate to intercept any surface water flows, and have crossfalls and so forth to make sure that water is taken away and doesn't stand there for long periods of time, which is then able to infiltrate the clay fill. If you have internal water flows, then it's best to intercept them with a gravel drain at the back and base of the reinforced soil structure, or the soil structure in general. That would be a very important detail. Again, possibly with an exit pipe to try to make sure that that drainage layer remains empty. Also, at the back there, when you have a back of, or you have a gravel drain at the back of the reinforced soil block or the compacted fill, it should not daylight. It's a common mistake that you will see. People often put these drains coming out at the top. And if you do that, what it means is that the surface water can nicely run down that drain and come out at the bottom, therefore giving another big potential for the clay fill to absorb water and soften, which you don't want to happen. Also important that the internal drains should be arranged to remain empty. You don't want them sitting there full of water. Just remember our friend Clay and what he asked. He said, please don't put me in contact in the long term with free water. So these are some of the principles which I feel are very important when you're designing drainage in conjunction with clay fills. Now, there are forms of geosynthetic which combine reinforcement and drainage. Now, is this a good idea? And I'd have to say, as with any engineering material and decision, it depends on the design situation. But in a simple way, if a mass of clay is in a state of suction, then the only possible result of including thin drainage layers throughout that clay would be provide a path for water to enter the fill. And if it did that, this could cause swelling and softening. And it's just a thing I often like to ask people to think about, to remember that when you create a drainage provision or detail designed to let water out of a system, then if things go wrong, it could let water go into the system, which you don't want to happen. So just think carefully about that. But I want to show that the last thing I'm going to cover today is using an example from a project in the UK on the London orbital motorway called the M25, where an interesting failure took place. And let's try to understand what happened. I was actually involved in investigating this failure. So I had some first-hand experience, and the photographs we're going to see were taken by me at the time. There is a very detailed report about this published a long time ago in the proceedings of the ICE. And particularly important, there was an extensive discussion. And if you really want to learn a lot about this, the discussion probably is almost more important than the original paper, but you can see there the discussion was, what, 24 pages of it. So very important document. The failure occurred in June of 1981. I've already mentioned it was on the M25. And there, without a doubt, there were some very important lessons learned, especially concerning drainage blankets and the importance of avoiding creating a water source in contact with a compacted clay fill. Just think about our friend Clay again, our packed clay. So let's have a look and see what happened. The site was like this. We're looking along or down the center line of the highway. And in this particular part of the site, there was a slight crossfall from left to right. So what they did, they placed the drainage blanket directly on top of the topsoil and the grass. And in this case, the drainage blanket was not actually that higher permeability, if you look at the numbers there. And almost certainly as it sat there, it became saturated with rain. And then, as is often the case with earthworks, the contractor suddenly got very busy, and he managed to place all of that London clay fill in a 10-day period. And at the highest point there, it's something like 12 meters high. So a huge amount of clay placed extremely quickly. And unfortunately, within a short time after completion, it starts to fail. First of all, it was noticed straight away, but just after 2 or so days after the first cracks appeared, the toe had moved out by about 3 meters. And because this was a rather serious situation, which no one really expected, a significant investigation was carried out, which included building a small trial embankment, which we'll look at in a minute. So here's one of my photographs. When I first arrived at the site, you can see very clearly there the failure. And investigations had just started. There's already someone, I think, doing a borehole up there somewhere. The usual kind of thing that goes on in these cases. You can see how the toe of the embankment has broken down the fence at the edge, which means that the embankment is now moving into the property of the farmer on the left-hand side, so he'd be very happy that that's happening. And what was rather nice here, and I showed this picture many times because it's just so interesting, is that a little trench was dug into the toe of the embankment, but possibly by mistake, it was dug at a slight angle, which meant that you could start to see the appearance of the sliding surface between the clay above and in this case, you can see the drainage blanket material there at the bottom. And clearly this required some thinking, what should happen. So it was important to understand about the pore pressures and what happened with the drainage blanket. So one thing that was done, some very detailed profiles of water content were made, literally taking samples at very, very small spacings, just millimeters above the drainage blanket to look at the distribution of the water content. A careful look was made at the grading and permeability of the drainage blanket. But then what was very interesting was that nearby, there was an existing section of embankment which had only reached 4 meters high. And so it was decided to install some piezometers into this and then place another 4 meters of fill very quickly. And this was referred to as the trial embankment. So it looked like this. So there was this existing section of embankment, 4 meters high, and they placed they placed these piezometers. There are 3 of them shown there, and in this case you've got P8 in the bottom of the fill, P7 is in the drainage blanket, and P6 is in the top of the foundation soil, which is also London clay. They very quickly built 4 meters of fill as quickly as they could to try and imitate what had happened. And then we have here a record of the performance against time. So the horizontal axis is the time in days, going up to 80 days. And the elevation, in this particular case, is showing the location of the drainage blanket and also the top of the embankment fill. So you can see the original 4 meter height. And then in a really fairly quick time, they build up another 4 meters to reach a total height of 8. So what I'm going to do now, I'm going to superimpose on this diagram the pore pressure responses in P8, P7, and P6. And they look like this. And it's worth just studying this diagram because as you start to look at it, it doesn't seem to be right, because P7, the colors match. P7 is the brown color. That's the piezometer in the drainage blanket, and it has the highest pore pressure. The pore pressure reaches that height. It's an elevation. Whereas at the top of the foundation soil, the green line has a slightly lower pressure. But the weird thing is that towards the bottom of the fill, we have a negative pore pressure, because of course this was London clay, built to very good specification of achieving an undrained shear strength, and it had a high suction in it. And that's what we're seeing in the piezometers. So it's a bit difficult. So the obvious question is, well, why wasn't the drainage blanket at 0? Why wasn't it empty? Well, it was very, very wide. and of a rather low permeability, and it really wasn't working very well. You can see it does slowly dissipate. The brown line does start to go down, but it does it slowly. So let's go back to the cross section. There it is. You can see the sort of information they got from the measuring the profile of water content. Normally, water content was something between 17 and 33%, but just above the drainage blanket had softened a lot, and it was 40% or more at those elevations. So what was going on was that the high suction in the base of the fill was absorbing water into the base of the clay, contributing to the problem which took place. So what happened, and this is mainly or partly my own kind of picture of what probably happened, is that we have a foundation soil, the field lying there, and probably the top of the foundation soil would have low suction values before construction started. Then this rather low permeability drainage blanket was placed, sat there for quite a long time in heavy rain, and it got saturated. So the pore pressure currently 0 before any fill is placed. Then the fill is built very quickly and with very high suctions over the top. So what happens is that the drainage blanket with its high pore pressure then provides water to the base of the clay fill. And when it softens sufficiently, the strength reduces enough, even on that very gentle slope, to create a failure. And the failure took place either just above or below the drainage blanket, either in the base of the fill or the top of the foundation. There was a geotextile separator placed above the granular layer. It didn't by itself contribute to the failure, but the problem was it gave a rather plainer surface, making it rather easier for that sliding to take place. And if I go back to this diagram and I plot that information, the solid green dot is the base of the clay. You can see how it matches the typical behavior we'd expect from a clay fill. And you can also imagine that near the top, it would be a much greater suction than we see down at 8 or 9 meters. And then the open green dot is the behavior in the drainage blanket. So I've come to the end now. We've covered quite a lot of information, but just to remind ourselves about a few things, then in a well-compacted clay fill built to typical highway specifications, then the clay is going to be in a state of suction to considerable heights. Very high fills you may generate positive pore pressure at the base of the fill. However, in typical highway embankments, generally not reaching those heights so often. And of course, these suctions provide additional safety factor, which we don't normally take into account in our calculations. So it's a kind of bonus, but because it's there, we don't want to lose it. I've already mentioned that only for very high or for high fills are you likely to generate positive pore pressures towards the bottom of the fill. We saw that earlier on. If you are going to generate, in fact, in most cases, it's best to use a basal gravel drain, especially if you're in a situation where you might have high pore pressure towards the base of the fill. And it's important that drainage measures should be arranged to avoid prolonged contact of the fill with free water. Just remember Pat Clay and his requirement to avoid him being in contact with free water. And drainage blankets should be arranged. They should have crossfalls and be in locations where they can essentially remain empty. In other words, water can easily run out of them. They don't sit there providing a source of water to the clay nearby, like we saw just now with the Hill Hall failure. These are the main references I used. There were probably a few others, like the books earlier on, where you can see the covers of the books. That's where my information comes from. So that's the end of this particular webinar. I'd like to thank you for your attention. The June webinar, I've already mentioned the topic is going to be a significant change. We're going to talk about using CPT in soft soils. Also, just to make a mention here that we seem to be these days in the world of webinars, but we on a rather different topic, but related. We shall be holding a webinar next week where the aim will be to look at a particular design program called Tensar Soil and look at the design of reinforced soil slopes. So in fact, some of the things I've been talking about today will be rather relevant as background information to that particular talk. If you have a mobile phone and you scan that QR code there, then that will give you a link straight away. But I think a link will also be provided by Multi-Bangren as well, if you would like to join that. So this is much more a design workshop, looking at a particular piece of software, which many people here in Indonesia have for use themselves, to see how we can design reinforced soil slopes. So thank you again for your attention.